Welcome to the channel Forensic Science Public Desk India. Topic is Basics of Forensic Chemistry, presented by me, Mr. Praveen Torati. Module 3, Basics of Atomic Structure and Applications. Third module is going to cover Introduction, Periodic Table, Atomic Structure, Electron Sharing, Electron Configuration, Mole and Molar Mass. Introduction. Before we proceed further into the atomic structure and understand the periodic table, we have to know about these three people, that is Dmitry Mendeleev, Lothar Meyer, Henry Moseley. In 1869, a Russian chemist named Dmitry Mendeleev discovered that elements exhibited a repeating pattern of properties. When organized in order of increasing atomic mass, he called this observation as periodic law. Then we have the German chemist Lothar Meyer also observed the atomic periodic relationship around same time. But as fate would have it, Mendeleev is credited with discovery because he was the first to organize the elements. The current form of periodic table was later discovered by Henry Moseley, who observed that elements organized by increasing atomic numbers created a more uniform arrangement. The periodic table plays very important role to understand the chemistry in basics, and this basic understanding is also required for understanding many of the concepts in forensic chemistry. Periodic table of elements. In periodic table of elements, we'll be having all elements which are to be discussed in chemistry and forensic chemistry. So these elements are represented by the symbol. So this is a symbol. H is a symbol of hydrogen. Ni is symbol of nickel. So on, we are having symbols for all the elements. So the easiest part to remember these elements, their initial letters will be mentioned as the symbols. For example, you can see gallium here. Ga is mentioned as its symbol. So similarly, we are having the same type of symbols for all types of elements. But few times we can see this silver. Ag is a symbol for the silver, and Au is a symbol for the gold. Why? These particular names, for example, gold name is aurum. So Au is the given symbol for the gold. Similarly, we have to remember few of those names. Coming to the contents of the block, we can see atomic number. So atomic number will be placed on the top, and its element name will be mentioned in the low under the symbol, and number electrons per shell is mentioned in the very bottom, and the atomic weight is also given, that is the mass weight. So all these things are mentioned in the block. These are the basic properties of that particular element. So the elements are arranged in the periods and groups. So these are the groups: 1A group, 2A group, 3B group, so on. We are having 8A groups. So 1A groups are called alkali metals, and 2A groups are called alkaline earth metals. So then we are coming to 8A group elements. These are called inert elements. Then we are also having 7A group elements. Those are halogens. So these group elements we have to remember very carefully, because this particular group elements are going to show similar chemical and physical properties. Similar in the sense, not so similar, but they are having a class characteristics, so that they can be grouped into one type. So based on these things, we can understand the periodic table. So further understanding, we can see here state of matter, color of name is given as gas. So hydrogen, it is given its name in red color, so you can understand it is a gas. So liquid, if you want to see the liquid, bromine is the liquid, it is shown in the blue color. And solids, so most of all these transition metals, so third B to 2B, this type of all these metals which are there in between are called metals, and those are solids. Then lanthanides and actinides are metals, and they are the elements which are also there in the periodic table. But for our forensic chemistry interest, the 1A, 2A, 7A, 8A, and 3A, 4A, 5A, 6A are going to be very important. So electronegativity will also be increasing from the left to right. Atoms are the smallest indivisible unit of an element that retains all chemical and physical properties of the element. For example, a single atom of gold has same physical and chemical properties as 10 tons of gold. So our atomic structure, we are going to discuss about proton, neutron and electrons. So these atomic particles are going to contribute for the structure of atomic, and atoms will be having positive and negative charge. Positive charge is carried by the protons and negative charge is carried by the electrons. So protons and neutrons together, they are binded and they are going to form a nucleus. As we can see in this image, it is forming a nucleus together of proton and neutron. So this proton and neutron are only going to contribute for the weight of the atomic structure. So here the atom mass unit is 1.66 into 10 to the power of minus 24 grams. So this one atomic mass is this. So the protons number, how many protons are there? So that number is called as atomic number. So if you want to know mass number, that is protons plus neutrons. So protons and neutrons are going to form the mass number, and alone protons are called atomic number. So minusing, that is subtracting atomic number and mass number, we will be getting the neutrons. If there is any difference in the number of neutrons, then they will be forming isotopes. If there is any difference in number of protons, there will be change in atomic number, and if there is any change in number of electrons, it is going to change the charge on the atom. The overall charge on the atom is determined by comparing the number of protons to the number of electrons. If the number of protons is greater than the number of electrons is greater than number of protons, the atomic number, the atoms carries negative charge. If number of electrons is less, the atom carries positive charge. If they are equal, the atom is neutral. The net charge on the atom in its standard state, that is natural conditions, is always 0. So we are having example of sodium here. Sodium atomic number is 11. That means it is having 11 protons. And if it is want to be stabilized, or it wants to maintain a stable state, it should be having 11 electrons. So this is a natural state of sodium. So sodium is having 0 charge now. So we are going to remove one electron. Let us assume that we have removed one electron, so that it will be carrying a positive charge. Instead of removing electron, if we are adding one electron to this particular atom, it is going to become negatively charged. So like that, the electrons which are all around the orbitals, this will be added or removed to obtain the stability. So that will be discussed in arrangement of electrons. Lower energy electrons are closer to the nucleus, and obviously higher energy electrons are far away from the nucleus. So whatever the energy is there, if the electron energy is lower, that will be closer to the nucleus, and whatever the energy is larger, that will be away from the nucleus. So this will be giving the tendency of to the electrons whether to escape or to accept the electrons. So this is all depends upon the amount of energy carried by the electron. Only energies are allowed are called quantized, or energy determines the location. So the amount of energy the electron is carrying, that much the arrangement of electrons is based on that particular way. Principal energy levels are further classified into suborbitals as S, P, D and F, helps in identify the electrons of specific energy. So we can understand this concept in a example of hotel. If hotel is there and you are the manager and you are getting the customers, so first customers you are going to fill it in the first orbitals, and let us just imagine assume that these first customers are of lower energy, and as going on, as the customers are increasing, the energy of the customer is also increasing, and you are going to place it in the outer orbitals, and coming to the top level orbitals, you will be having very few electrons. So according to the number of electrons, that means according to the natural state of an atom, you are going to place the electrons in different levels of orbitals. So we have understood that electrons are not arranged randomly around the nucleus. They are arranged in a pattern. So according to the amount of energy the electron is carrying, it will be placed in different locations on different orbitals. So subatomic orbitals we have already discussed, those are s, p, d, f. So main energy levels we are having four. 1, 2, 3, 4 main energy levels are there. To that sub levels will be there. For one main energy level we are having s. So for S, maximum number of pair of electrons will be 1. One pair of electrons, that means 2 electrons will be there, and maximum electrons in the level total is 2. So main energy level will be containing 2 electrons. Similarly, NH2, when we are coming to main energy level 2, we are having S and P as sub levels. So S is having one pair and P is having three pairs. So similarly, you can see P is having three pairs now. Here D you can see five pairs and F you can see seven pairs. So you have to remember this SPDF. In fourth level you will be getting all four, three you will be getting three, and two you will be getting two. So like that number of pairs you can remember, and for each pair obviously there are two electrons, and 2, 2 and 6 and 10 and 14. So basic things, if you remember these things, you can easily understand the electronic configuration. To form proper electronic configuration, we have to obey Aufbau's rule. So Aufbau rule is like you have to write the 1s, 2s, 3s like that, all s 1 to 7 and 2 to 7, 3 to 6, 4 to 5. This is a assumption of triangle. This is called Aufbau's triangle. If you write like this, you will be getting the sequence how to write electron configuration. So first 1s, then 2s, 2p 3s, 3s 4s, 3p 4s, 3d 4p 5s. So like that we are going to write the main sentence of the electronic configuration. This is the 1s, this is 2s, this is 2p, this is 3s. So on each suborbital, that is each sublevel, we are having electrons, number of electrons. See here in the table, maximum number of electrons in the sublevel 2 is there, that means 2 should be written. So let us take the example of sodium. Sodium is having atomic number 11 and it should be written in the electron configuration. 1s is having 2 electrons, 2s is having 2 electrons, 2p is having 6 electrons, and 3s is having 1 electron. So this is stabilized, this is written in electronic configuration. Electronic configuration will help us to understand the electronegativity and to understand the stability of the atom. So we are having few others here examples. So if there is lithium, it is having 3 electrons. It is mentioned as 1s, 2s. Here 2 electrons are filled, here 1 electron is filled. So 11, 2 plus 2 4, 4 plus 6 10, 10 plus 1 11, 19. So in potassium 2 plus 2 4, 4 plus 6 10, 10 plus 2 12, 12 plus 6 18, and one more, that is the 19. So all these lithium, sodium, potassium, you have to observe one thing here, that is in their valency orbital, suborbital, they are having one electron left out. That means these particular atoms which are there, they are belonging to 1a group and they are always ready to donate an electron. So similarly, we are having the 2a group, that is alkaline earth metals. In their valency, they are electrons. Only 2 electrons are there. 2 electrons for magnesium, 2 electrons for beryllium, and 2 electrons for calcium. So they are ready to donate 2 electrons. So similarly, we can see iron and chlorine. So they are having 5 electrons in their valence. They are ready to donate 5 electrons, or they are ready to accept certain amount of electrons. So this all gives us the properties. So if you understand the electron configuration, it will be very easy for us to understand the chemical properties of the elements and the group of elements. So here is the example of sodium chloride. Sodium has one valence electron, that means ready to donate one electron to stabilize itself. Sodium forms a molecule with chlorine called sodium chloride, where chlorine atom was deficient of one electron. The mutual balancing of electrons will form bonds. Sometime the elements stay neutral by maintaining certain charge, like to achieve octet rule. Metals lose electron, non-metals gain electrons. This thing you have to remember. So if in the periodic table we have seen 1a group elements donating 1 electron and 2a group elements donating 2 electrons. So like that we can see natural state and most stable state of different atoms. So natural state of sodium is 11 electrons, but it is more stable when it is losing 1 electron. So similarly we can see natural state of magnesium is 12 electrons, but most stable state is 10 electrons. So natural state of aluminium is 13 electrons, but most stable state is 10 electrons. So all 10 electrons are maintained by magnesium, aluminium, nitrogen and oxygen, but in the case of sodium, magnesium and aluminium they are donating electrons, but in the case of nitrogen, oxygen and ferron they are accepting the electrons, they are taking up the electrons of other atoms. So this is how they are maintaining the 10 electron rule. This is here 10, this is here 10, this is here 10. That means they want to maintain the 10 electronic configuration that is of neon, that is belonging to inert gas. So all the elements which are present in all the groups except one 8a, they want to become octet rule and they want to stabilize themselves. So this is the configuration which we can write. For nitrogen carrying negative charge 3, it can be written 1s, 2s2, 2p6, similar to all. So this is how the electronic configuration which can be written for the ions. So once electrons are lost or gained, that will be called as isotopes. Atoms that contain the same number of protons but have different mass numbers are called isotopes. Isotopes of an element differ only in number of net neutrons contained in the nucleus. Atomic nuclei are most stable, but when they contain certain number of protons and neutrons. The addition of neutrons to the nucleus increases the mass of the atom and creates instability. For example, the most abundant form of hydrogen contains single proton in the nucleus. The addition of the neutron to hydrogen nucleus creates an isotope of hydrogen called deuterium. Deuterium is heavier and most energetic form of hydrogen and is therefore less stable. The addition of second neutron creates a third isotope of hydrogen called tritium, the most unstable and active form of hydrogen. The instability of isotopes is direct result of increased nuclear mass and is detected through release of energy called nuclear radiation. The nuclear radiation is also called as radioactivity. The relationship between energy and stability is common thread that unifies most areas of science. High energy translates into instability and there is always natural tendency towards lowest energy and greatest stability. This inescapable, however, the response of an atom to high energy is not much different from our own. It will not remain unstable indefinitely. Eventually, the nucleus will emit energy in effort to regain the stability. Spontaneous emission of such high energy nuclear radiation from unstable nucleus is termed as radioactivity. So, all the atoms which are above 90 atomic number are exhibiting this radioactivity naturally. Early experiments identified three types of nuclear radiations, that is alpha, beta and gamma. These radiations can be understood by a small experiment where the radioactive substance is placed in a lead box with a hole. The radiation obviously it is released out of the box and it is projected outside. The radiation which is projected outside is applied with positive and negative charge of electric and magnetism. Any of these two can be used and obviously positive charge is attracted by the negative particles and those negative particles as named as beta radiations and the positive charge particles are called alpha radiations. So by this we can understand there are two distinct radiations and in between there are neutral particles also called as gamma radiations. So these three spots are being seen on the X-ray film and we have understood that there are three radiations of radioactivity. Radioactive isotopes will lose intensity, gain stable over time because of alpha, beta and gamma decay. The amount of time required for radioactive intensity to decrease by half is called half-life. So this is applied in anthropology, and we can study the age of any organic material. All organic material are containing carbon in common. So carbon 14 is considered as one of the radioactive isotope of half-life, which will be of 5720 years. So 5720 years is half-life of carbon 14. A 100-gram sample of radioactive substance of carbon 14 will remain 50 gram of active carbon 14 in 5720 years. 25 grams after additional 5720 years, and so on. So like that, by after every 5720 years, they will be decreased into half size, half weight of the carbon 14. So so that we can understand various organic chemicals, organic compounds which are there in the nature. The mole and molar mass. The mole allows scientists to understand the number of elementary entities, usually atoms or molecules, in certain mass of a given substance. That means a mole is having Avogadro's absolute number, that is 6.022 into 10 to the power of 23, and the units which are given is atomic mass number. So there are no other further units which are given to this. If there is one atom of carbon, it is having atomic number 12, but the whole carbon atom Avogadro number is 6.022 into 10 to the power of 23. That is the elementary entity. So if there is a particular matter, let us assume the example of water. Water is containing two hydrogens and one oxygen. So its atomic weight is 18.015. So, and its Avogadro's number will also be similar to that. So hydrogen is one atom 6.00022 into 10 to the power of 23. Like that, there are three elements which are containing these things. So simple basic understanding. One example I can give, that is, how many bananas will be there in one dozen of bananas? That is 12. So 12 bananas again is equal to dozen. So like that, the atomic mass unit of water is 18.015, and what is one mole water weight is 18.015 grams. So that is the thing. So you can completely avoid 6.022 into 10 to the power of 23, and you can just remain, you can stick to the atomic weight of the element. So you are considering the atomic mass units, and you are giving the weight of the element. That means the molecule, water molecule, its weight and its atomic mass. So the atomic mass of any element in grams contains 0.6 6.022 into 10 to the power of 23 atoms of the element, or 1 mole of element is called molar mass. So this is given by Avogadro. He is an Italian scientist from 19th century. We have discussed clearly about the periodic table and its basic, and we have also understood atomic structure and its subatomic particles, and how electrons are shared in the atom, and how they are arranged, and how to understand the arrangement in the form of electron configuration, and what are Aufbau's principle, and what is octet rule we have discussed, and we have also understood what is mole and molar mass. I hope you have understood everything very well. Thank you.